Kyle is our next speaker, joining us from University of Arizona. He's going to be talking about ongoing work using SU2 for hypersonic applications. So this is the NEMO group that you all probably know about. So take it away, Kyle, whenever you're ready.
All right. Thanks for your introduction. So I'm going to be talking about some of the ongoing work we're doing at the University of Arizona using SU2, both SU2 standard and also SU2 NEMO for some high-speed flow applications. So advancing to the next slide, our group at Arizona is called the Computational Hypersonics and Non-Equilibrium Lab, and these are probably two of my favorite figures and motivate why we do what we do. So on the figure on the left, and hopefully you can see my cursor, but we see hypersonic flight and some reentry trajectories. And as you go through these certain trajectories, you see different physics present themselves from, vibrational excitation, different energy modes becoming active to chemistry and even ionization. And then if we look here in the middle figure, we look at what experimental facilities can do these type of experiments. And we see shock tubes can reach a wide range of enthalpies. But if you look at the testing time, it's on the order of microseconds. So we'll see later in this talk, this is good enough for, validating and assessing chemical kinetics. And then as you work your way on testing time, you actually stay pretty low in enthalpy, but you're able to get, more, flow field definition, aerodynamics, and even some material response. So kind of what I'll talk about in our talk is what we're looking at in chemical kinetics and what we're looking at comparing to blowdown tunnels and with hope of, extrapolating or using NEMO capabilities to look in this region of what it would actually be during hypersonic flight. So I won't go into too much detail about SU2 NEMO. Marco has presented to this group many times, so it's one of the codes, that we're using in our group. And this is with close collaboration with students at Stanford, Strathclyde, and VKI. And one of the benefits of SU2, at least what we like in our group, is its coupling to mutation plus plus. So historically, we've always fit different chemical kinetics models into different codes, whether that's, heat baths, LES codes, fluid structure interaction codes. So we end up doing a lot in different locations, but with this coupling here, our goal is to only add chemical kinetics models to mutation plus plus and then pull them into SU2. So chemical kinetics, this is a lot of work done by a student in our group called, his name's Aaron Larson, and he's looking at state-to-state modeling. Specifically, we're looking at vibrational state-to-state modeling. So instead of modeling different chemical species, we're picking a species. And in his case, we're looking a lot at oxygen, and we're looking at different vibrational levels of oxygen. So it's different ways you can discretize your vibrational levels. And what we use is rates. So we have bound rates. So this would be a rate of how quick you go from level 1 to level 2. And you also have bound free rates. And these bound free rates, would go from 2 to dissociation. So you'd have O2 dissociating to O atoms. And one of the challenges with this project is that these rates come from quantum chemistry, and we're not always on favorable energy ladders. So he's working on some mapping to map it from, maybe a 36 level ladder to a 46 level ladder. And this means a lot when you're trying to do, multi-species flow. So a lot of what Stanford does and Hansen's shock tubes is maybe oxygen diluted in argon. So this would be 2% oxygen and argon. So as soon as you add in argon at species, you need to also include, argon O2 interaction. So that motivates this mapping approach. And what he has been working on is, moving this into mutation plus plus. And we've been running some state to state with SU2 shown here. And along these lines is we have our shock tubes. So we're assessing with shock tubes. And we're trying to actually run the full experiment that we're doing at Stanford with SU2. So historically, we have a reflected shock tube. So in region 5 would be a stagnated gas. So we treat that as heat bath. So, usually what we do is just treat that as a 0D heat bath, try to neutralize it and see how it behaves. But, what we're trying to do to actually assess if that heat bath is an appropriate assumption is running, a full shock tube, reflected shock tube region. So you can see a high pressure, low pressure region, and then you see a reflected shock wave coming back. Should be advancing to the next slide. So another case we're looking at is aero optics. This is with Leif, Gohar, and Martin. And aero optics is a pretty good application to show, where we can, collaborate with these low enthalpy experiments. And I kind of split this up into quadrants. So historically, aero optics is low enthalpy flow, so no chemical reactions. And then what we're looking at is what happens if you have chemical reactions. So if you do have chemical reactions, your Gladstone-Dale constant is going to change. So it's no longer constant, it's a function of temperature as you have these chemical reactions. And what we're really trying to utilize SU2 for, besides just chemical reactions, is starting to explore quadrant 4 and quadrant 2. And this is starting to look at high flow resolution. So we're trying to get some LES going to be able to get some, pore side error, uh, optical path differences that you can't do with a regular RANS run. So we've been able to run a lot in quadrant 1 and quadrant 3, looking at low enthalpy and high enthalpy, RANS or lambda type simulations. But now we're really trying to look at the turbulent fluctuations. And this is with a project with Notre Dame, and we're using our hypersonic wind tunnel. And what we're doing is looking at transitional features over a shape like this. So we use SU2 to design this shape in collaboration with some linear stability theory. So we run, a lot of base flows. We pass that off to linear stability theory to, do analysis to see, what shapes are going to result in, transition to turbulence. So this resulted in us creating we started with a shape like this. And with a few iterations, we realized we need a sharper nose and a wider angle here to be able to get those transitional features in these wind tunnel conditions. Propulsion, I won't go into too much detail here, but we've also used SU2 for some of the solid fuel ramjet project that we're on. This is in collaboration with the UMBC and China Lake. And this project is to regulate thrusts in the solid fuel ramjet. Typically, this is really hard to do to actually regulate and control thrusts. So the UMBC collaborators are developing a controller, but this controller needs to be in tune via simulations to actually replicate what will happen. So we're looking at it with analytical theory, but we're using SU2 RANS primarily to look at solid fuel ramjets, and I have a slide on that to show where we are. So it would be really nice to use some of the features of a previous talk by Lisa to do some of its combustion modeling, but we're starting at ground zero, and we're just modeling the combustion by adding a heated wall. So as you add heat flux, we're able to get a thrust response. This is sent to a controller, but we're hoping to take it to the next step in year 2 to look at chemical reactions. Plasma flows. So plasma is a nice feature that we have within SU2 NEMO. We're able to get chemical reactions, and with those chemical reactions, we're able to extend it to ionized flow as well. And one of the projects that our group is most well known for is electron transpiration cooling. So this is where we're emitting electrons from a surface. So we have a term of electrons from the surface to provide cooling. And this is another feature that we hope to have added to SU2 NEMO later this year. So have a boundary condition to have electron transpiration cooling. Advanced slide, hopefully. Aerodynamic heating. This is another area that we're collaborating with, multiple wind tunnel partners, so both at Notre Dame and the University of Arizona. University of Arizona has 2 blowdown tunnels, so we're able to look at some of physics with standard NEMO and be able to extend it into higher enthalpies with SU2 or with the NEMO capabilities. A couple challenges that we've been running into, at least compared to some of the previous codes we've used, is SU2 for these high speed flows so Mach 5 hypersonic, has required a pretty small initial grid size to be able to get accurate heat flux predictions, and just small cell size, in our experience, has hurt conversion. So this is something we're exploring to try to improve. It'd be nice to be able to get away with 1 e to the -6, 1 e to the -7 for that, especially for some of the complex shapes, thin shapes that we're looking at. So we're always open to help in this area or any of the previous areas. And we're also exploring various viscosity models to accurately calculate the transfer properties. So these low enthalpy wind tunnels, the free stream temperature are on the order of 50 Kelvin, 60 Kelvin. So it's extremely cold. Sutherland's law breaks down at those temperatures, but that's what people use, and we're looking at assessing the uncertainty with that calculation. So another thing, so I'm just going through a lot of the topics that we're working on, and one of the exciting ones we're working on is we're comparing some of the cases that AFRL is running with their potential energy surfaces. So they got a frontier project, and they're running direct simulation of their potential energy surface. So these take millions, if I almost say billions of CPU hours to be able to run some of these simulations, and we're comparing it with SU2 Nemo, looking at translational and vibrational. So we don't have rotational non-equilibrium in SU2 Nemo yet, but we're looking at least a vibrational comparison to this. So they have cases of Earth, global cones, and also of leading edges that we are looking at, and that will be presented at AIAA SciTech. We also have an uncertainty quantification project that we're hoping to leverage with some of SU2's capabilities. I'll advance this. And then looking forward, photonics is very multi-physics, and we think SU2 is perfect for this multi-physics environment. Here's some of current couplings. We're hoping to explore some of this in the coming years with fluid structure interactions to see how high enthalpy of flows impacts fluid structure interactions, and then also these would be some interesting future areas as well, looking at electromagnetic solvers and also material response as well. So this is a slide on fluid thermal structural interactions. So historically, what we put in wind tunnels is very rigid. It's not going to move, but what we fly hypersonic is very light. So it's lightweight structure. So you do have some fluid structure interactions, and we hope to be able to characterize what that high enthalpy effect has that you don't see in low enthalpy flows. And then meshing. We don't talk about meshing much in presentations, but in terms of man hours, this is where we definitely spend most of our man hours. So out of a motivation of looking at a lot aerodynamic heating, we've gone down a lot of structured mesh paths, and then we've also tried mesh adaptation, and we've seen some interesting results that I won't present here, but I hope to in future SU2 conferences break this multi-component presentation into a couple that we can go into more detail. So with that, hypersonics is complex and multi-physics, which we think SU2 is well suited for. We definitely love collaborative environment of SU2. We have a small team at Arizona, but be able to leverage ever developers at VKI, at Strathclyde, Stanford, and just the SU2 community, makes our lives a lot easier. And then I just have a list of some improvements, enhancements that we're looking at. So with that, I think I'm out of time, and I'd be happy to take any questions.
Okay, thanks, Kyle. That was very, very comprehensive. So I have to imagine there are questions. So we have a couple minutes. Anyway, I'll do my best to repeat the question just in case, or if you want to walk up and ask, you can walk up and ask.
I was wondering, what can you explain a bit more about this electron transpirating cooling? Like what some basics for how it works? Yeah.
Did you hear that one pretty clearly, Kyle?
Yeah, I think I heard it. So talk more about electron transpiration cooling.
Yeah, that's right.
Yeah, so if I can find the slide, and there's a little lag, but so these leading edges, hypersonic vehicles, you need to have a sharp leading edge to reduce the drag. But when you have a sharp leading edge, that results in very high heat loads. So one of the things that we've been looking at is a low work function material at leading edges. And essentially, we're going to convert that heat to electricity. And when you do that, you're emitting electrons into the flow field. But as soon as you do that, you open up a lot of physics. So we usually assume it's a quasi-neutral flow, but as soon as you emit electrons, it's no longer quasi-neutral. You have to worry about plasma sheaf effects. But what we're trying to see is if there's enough, collisions here to kind of drive electrons to, recollect on some at body and return to the surface. So this is kind of a comparison of ETC to radiative heat transfer. You can see if you have a low work function material, aka if it doesn't take much energy to emit an electron, it becomes really effective at high surface temperatures. And this black line would show, it's where it's just as effective as ETC. And I'll note that it complements radiative cooling as well.
Okay, thanks, Cal. Other questions? I have one, if you don't mind, is so you highlighted that grid spacing is an issue. Implicit methods, is that what you're gonna aim to get around that issue, or is there something else fundamental you can do? Like, are you just basing it on the spacing you need to capture heat flux at the wall, for example, or?
Yeah, to be able to get an accurate prediction of heat flux, it requires a very fine cell spacing. So I don't think the implicit solver will help with that. I mean, that might help with the time it takes to run. But I mentioned implicit solver here because when we have these chemical reactions, we're not able to ramp up the CFL. So usually the max CFL we can get is 1. So the implicit solver works, but we definitely like to improve it for the NEMO capabilities to be able to not be so limited in CPU power.
Yeah, yeah, you'll want a higher CFL. Josh has a question.
On the cover, it would be really nice to see this improvement in fair heat calculation evolve, like with the data solver as well. So it's a NEMO specific thing. Is that something that you find on creating?
Can you repeat that question?
Yeah, so you're saying getting the grains, the roots. Yeah, so I guess the general question, Kyle, is, of all the things you guys are working on, are there certain things that can be brought into the main branch? So kind of like core solver technology stuff. Are there any movements to bring some of this into the main, like, develop branch?
Yeah, I definitely the aerodynamic heating. So that's something we hope to fix or improve. I think it works for most cases. It's for some of our cases it becomes finicky because we're pushing the boundaries in terms of Mach number. But we see this showing up even when we run the standard NEMO branch. So whatever we find, we'd be happy to push into the main branch.
Okay, great. All right, we better move on. So let's thank the speaker again. Thanks, Kyle.